Welcome to Module 5. This module looks at atmospheric circulation. Topics that we'll look at in this module include weather versus climate, what is the atmosphere, what is the atmosphere comprised of, how does air circulate within the atmosphere, what is the Coriolis effect, what are atmospheric cells, and this actually plays a role in how air moves in the atmosphere, as well as we'll talk about storms. Why do we even focus on the atmosphere when we're doing a course in oceanography? Well, if we look at it, we see that the Earth's ocean and the atmosphere are intimately intertwined. What happens in the air, what happens in the atmosphere directly can affect what's happening in the ocean. What's happening in the ocean will affect what's happening in the atmosphere. We'll also see that atmospheric circulation plays a big role in helping to drive ocean circulation. First off, let's look at the difference between weather and climate. Weather refers to the short-term conditions of the atmosphere for a specific time and a location. So the weather could be, it's a sunny day today. Climate, on the other hand, is the average daily weather for an extended period of time at a certain location. So it could be saying it's summer in Wolfville, we can expect it to be warm, sunny, and slightly muggy some days, or humid some days. So weather just talks about sort of a short little period in time, almost like a snapshot. Climate is more sort of the overall album, or all of the pictures, what happens throughout an entire longer period of time. Climate is what you can expect, what you can predict. Weather is what actually happens. So climate and weather are not interchangeable terms. They are not the same. Weather refers to the short term, the daily conditions. What's the weather today? The climate, do we live in a cold climate? Do we live in a warm climate? Do we live in a tropical climate? It's more of a statistical view. What's the overall sort of daily weather patterns like? Before discussing atmospheric circulation, we should actually look at the Earth itself, look at how the Earth orbits around the sun, and why does Earth have seasons? Because we know that seasons play a role in what our climate is. Our climate tends to be cooler in the winter months and warmer in the summer months. Why does the Earth have seasons? Well, basically it's because the Earth's axis is tilted. It's tilted at approximately about 23.5 degrees from vertical. So this tilt causes seasons. There's times of the year, for example, the northern hemisphere is pointing closer to the sun. This corresponds to our summer. We're pointing closer to the sun. It makes sense that temperatures are going to be warmer. Other times of the year, we're going to be pointed further away from the sun. And then that's when we have cooler weather. So we have less sunlight striking the Earth during this period of time. We experience a cooler climate. And that explains seasons. As the Earth rotates around the sun, what we see is sometimes we're pointing closer to the sun, sometimes we're pointing further away, and this gives us a seasonality, especially at the northern and southern poles. If we get closer to the equator, we find that the distance from the sun is less throughout the year. The fact that the Earth has a tilted axis means that there's an unequal distribution of sun over the planet. So let's take a look at this little diagram here. Imagine that you're in either the northern or the southern hemisphere. Sometimes the year pointing towards the sun, sometimes the year pointing away from the sun. We're going to consider in this case that we're actually pointing towards the sun. What happens if you're in the more northern latitudes or southern latitudes is a couple of things. There's actually more atmosphere between you and the sun. The sun actually even strikes at a lower angle because of this tilt. So if you take a look at this, we see that we have a 1 square meter solar sunbeam shining on the Earth, and we can see that the area that it hits, the area that it covers in the northern hemisphere is pretty great. The other thing that happens in the northern and southern hemisphere, especially in these higher latitudes, is that we have snow and we have ice. Sunlight hits that snow and ice. It's white. It actually is going to be some of that radiation, some of that energy from the sun is going to be radiated or reflected back into space. So in the northern hemisphere, more atmosphere. It means that the intensity of the sun's rays that are hitting a person at that point are decreasing. Sun is striking at a low angle. That means that for a 1 meter square sunbeam, it has to cover a wider area, warm up a wider area. And we have the reflection of the sun off of ice and snow, something that's called albedo, the albedo effect. If you look at this in comparison to someone who's standing on the equator, right in the middle of the Earth, what happens there is the Earth is fatter there, or wider, so there's less atmosphere between the Earth itself and the sun. And the sun actually hits the Earth at a higher angle. Once again, we're using a 1 square meter solar beam. And if you look at the area that's covered by it on this diagram, we see that it's much smaller. So that area picks up a lot more of the sun's intensity, a lot more of the heat. So this is another reason why we have this irregular heating of the Earth's surface, is that we have more intense sun, it's hitting at a more direct angle, covering a smaller area, less atmosphere of the tropics, and then as we move to the more higher latitudes, either north or south, that same size of sunbeams covering a wider angle is at a lower angle, has to cover a much wider area of ground, more atmosphere behind it, and we're reflecting back some of the sun's rays. And remember, it's solar energy, this radiant energy from the sun, and changes in it that causes variations in the global sort of ocean atmospheric circulation patterns. So if we were to summarize the previous slide, what we see is in the northern hemispheres, the sun is reflected. We get less sun energy there than the amount of sun received. Less energy is making it to the Earth. In the tropics, away from these more northerly and southerly latitudes, we see the sun reflected is much less than the amount of sun received, and more energy is making it into the system there. So what happens is we have an unequal distribution of heat throughout the Earth. So this unequal distribution of heat, or more correctly solar energy throughout the Earth, means that we see sort of an area where we have a net heat gain, once again the tropics and into sort of the lower latitudes. And then in the oceans, the higher latitudes, the atmosphere at the higher latitudes, we see a net heat loss. And this results then, because we have to maintain we have to balance on an overall heat budget for the planet, is that extra heat gained in the more tropical regions is going to be transferred from the equator towards the poles, and this creates a circulation pattern. And we can see the circulation pattern in the atmosphere, and we'll get more into what's going on in that in a few moments. To summarize it, what we see is the atmosphere transfers heat and water vapor from place to place on Earth. So that excess heat result is solar radiation. Water vapor, we'll talk about why there's water vapor in a couple of minutes, that gets transferred from the equator in the mid-latitudes over to the more higher latitudes in both the north and the south. Polar regions lose more heat, tropics gain more heat, but what we see at around 38 degrees on both sides is this balances out. So let's take a look at the composition of the atmosphere and some of its physical properties. And one key thing to remember here is we're talking about the lower part of the atmosphere. The Earth's atmosphere is actually layered, and different layers have different physical characteristics and other properties as well. So what do we see? If we took a sample of air, what would we typically see? We'd see that the air actually is predominantly nitrogen. And remember that nitrogen dominates within the dissolved gases of the ocean. So within our modern day atmosphere, we're looking at probably about 78.1% nitrogen. Oxygen typically comprises about 20.9% of the total content of the atmosphere. Other elements and compounds less than 1%. And then there's water vapor, so the gaseous state of water. And we can find that it may occupy up to 4% of the air's volume. What we'll see is that air is never completely dry, or in very rare cases it's completely dry. There's always some water vapor in it. The water content, how much water vapor is held within the atmosphere in a particular occasion, as well as the temperature of that air, is it colder air, is it warmer air, is going to affect the density of the air. And if you think about it, we know that things that tend to be denser tend to sink, things that tend to be less dense tend to rise. What is the temperature of the atmosphere? Well, it's going to depend on where you are. So once again, remember that the atmosphere has layers. We see that the closer to the ground we are, sort of the lower layers of the atmosphere, we tend to have, the average normal temperatures that we associate, between minus 20 and 20 degrees. Let's say that's sort of on average throughout the world. As we move higher and higher, though, we see that the temperature decreases until we get to almost the top of the troposphere. And the troposphere is the lowest layer of the atmosphere. It's separated from the stratosphere by something called the tropopause. We see that overall the temperature of the atmosphere, the temperature of the air decreases, but then once it hits the tropopause, we actually see an increase in the stratosphere. and that would be an increase in the temperature. So we have air of varying temperatures present lower in the lower levels of the atmosphere. We know that we have warm air and cold air. What this means is we actually can have the potential to set up a convection cell. A convection cell very similar to what we discussed in Module 2. Warm air tends to be less dense. And we know that as when we talked about water, as things warm up, the molecules start to vibrate quicker. There's more space between the molecules. That decreases the density. So warm air is less dense, and it's going to begin and start to rise. Cold air, on the other hand, we're packing more molecules in the same sort of area or in the same volume. That's going to become more dense and it's going to start to fall. So if we picture the Earth as like a closed room, what we see is that near the tropics, where we have that surplus of heat energy, things get warm. We're going to have warm air rising. The air is going to rise. It's going to start to move towards the colder polar regions, where it's going to cool down. It's going to become more dense and fall, sink, and then travel again back to the tropics, warm up, and the whole cycle is going to repeat itself over and over and over again. Heats up, becomes less dense, rises, cools down, becomes more dense, sinks. And there we have a convection cell or a circulation cell. So if you're still having a tough time picturing why cold air sinks and warm air rises, just take a look at this little image here. We see the same amount of space outlined by either the blue box or the red box. Colder air, we have more molecules in there, they're moving a little bit slower, they're going to be denser. Hot air, same space, fewer molecules, are moving quicker. Now we have to consider water vapor, because we know that the atmosphere can contain up to 4% water vapor. The amount of water vapor that's being held in the air is going to be dependent on the temperature. The warmer it is, the greater the potential there is to contain or to hold water vapor. And that's because simply look at the two diagrams. There's more space for water vapor in hotter air or in warmer air. That's where you get those really hot, humid, sticky days in the summer. Warm air can have more molecules of water vapor. But wait, if we're adding water vapor to warm air, a package of warm air, wouldn't it start to sink? And what we have to remember here is that water molecules, the weight of them is going to be less than that of molecules of nitrogen and molecules of oxygen, N2 and O2. So it's still going to be less dense. Humid air is less dense than dry air at the same temperature. Once again, water vapor is less dense than nitrogen, N2 and O2 oxygen, so that warm air still is going to have a lower density and be able to rise. There's also something else that we have to consider, and that is we have to consider pressure. You imagine the atmosphere, really don't feel it, but we have a tremendous amount of the atmosphere sitting on top of us, and this is going to exert a pressure. The lower you are, the closer to the earth you are, the higher the pressure. So there's more of the weight of the atmosphere pressing down on you. But as you move up, that pressure decreases. And as a result, what happens is not only do we have that warm air rising, but that package of air is actually expanding because there's less pressure pushing down on it. So that as that warm package of moist air rises, less pressure is placed on it, and it's going to actually start to expand. And that's going to decrease the density a little bit more. The other thing that happens as that package of warm, moist air rises, it's less dense, and experiences decreased pressure, once again sitting on top of it, it expands, but as it expands, it actually starts to cool. And we know that cool air is going to sink. So what we see here, if you look at a very simple situation, we see it on the diagram here, is on the right hand side we have warm air, molecules are further apart, we have sort of what's called a low pressure system at the surface. We're going to have rising air moving away from the surface. It's going to expand. As it expands, it might travel through the troposphere and then begin to sink. It cools down as it expands. That air package is going to sink, fall back to the earth. We're going to have the molecules all packed closer together. That's why it's more dense. And this movement of air is what creates the wind. So here we have a very simplified version of what is going on. We have, in this case here, instead of the lounge, you can imagine this happening over the ocean. It would be a similar situation. We have that air parcel. I've been referring to it as a package of air. it sits there, it's heating up because of solar radiation to, let's say, as they have here, a temperature of 30 degrees. What's going to happen is it's warmer air, it's going to start to rise. It's less dense and cool air. As it rises, it starts to expand, and as it starts to expand, it cools down, both driven by the expansion and driven by the fact that we're moving further up into the atmosphere where temperatures are cooler. Finally, it's going to become cold enough where the density reaches a point where that air is going to start to sink, or that package of air is going to start to move down towards the surface of the earth or the ocean again. So as it does that, we start to increase the pressure on it. That's going to start to compress that package of air. We're going to pack more molecules into the space, further increasing the density, and it's going to sink down where once again that air warms up and the process replays itself over and over and over again. So we get this vertical movement of air occurring. If we take this concept that we saw in the previous slide and we apply it to the Earth itself, to the entire globe, what we see is at the equator and in the tropics we have a heat surplus. At the poles we have a heat deficit, and what we imagine then is air from near the tropics, parcels of air near the tropics are going to be warmer, they're going to be less dense, they're going to begin to rise in one of these convection cells and travel from an area of this hotter air up into the atmosphere where it cools down and expands. This corresponds to sort of that area over the poles where then it starts to sink and it moves back down towards the equator, towards the tropics. And what we get is we get these great big, what we think would be these great big convection cells operating in the atmosphere just above the surface of the Earth, the land, and the ocean as well. But there's something we haven't considered yet, and that's the fact that the Earth spins. The Earth is rotating, and this is going to play a big factor in these circulation patterns.